to the Maniac Talk. Today we have a special guest, our chief scientist. And before I get on to his story, I wanted to tell you a short story from Africa. And this is about three animals. Usually I like to use three because it's easy to remember. The first one is a hare. You all know a hare. And then the second one is a hyena, and the third one is a fox. Yeah. So the hare is going to have a big party. It's a wedding for his daughter. So he decides to invite all the other wild animals to this party. His chief guest, most important friends, the fox and the hyena. So on their way to this place, the hyena gets to a fork in the road, and then when he gets there, he tries to figure out which way should I go. Should I take the path that going towards the right, or should I take the one that goes to the left? So he's stuck there, not sure what to do. Tries to go towards the left, and then realizes, hey, if I go that way, maybe I may not make it to this big celebration for his friend. And so he goes back to the fork again, and then he keeps dancing around. So the fox comes around, and he says, "Hey, Mr. Hyena, what are you doing?" And he says, "Well, I want to go to this wedding, but I can't find my way." And then the fox, scratches the hand a little bit, and he figures out, I can feel the smell of the meat which is being roasted. And then he tells his friend, the hyena, that maybe we should go this way. And I said, no, I think it is coming from this direction. So, but finally, the fox now decides to leave his friend, the hyena, and takes one way. He uses 60 cents. The directions were not clearly provided, and then goes all the way to this place. And the hyena, in the meantime, is stuck and don't know how to move. Then, in the end, the hyena is going to see his friend coming back, and then realizes that, oh my gosh, so it must be on the right-hand side, the path that was going on the right-hand side. So he goes that way, and then he never waited for the folks to come and get the word that, oh, the party is over. So what does this story tell us? It tells us, and we used to use it that way, that in life, it is always very important to stay focused on one thing. Don't try to be in so many places at the same time. You can only do one thing. And I wanted to use that story to highlight the importance our speaker, Garvin, has done over the years. If you talk to Garvin, ask his name, he will tell you, my name is Mars. If you ask him, where are you going? He will tell you, I'm going to Mars. And if you ask him, where do you come from? He will say, by the way, didn't you hear I'm going to Mars? So today he's going to tell us his story. How did he get here? He's been here almost 30 years, and he has got very interesting stories about Mars and other things he's done. Obviously, as a chief scientist, he's done a lot. So please, with that short introduction, help me welcome our speaker, Garvin.
And now for something completely different. So yes, I do talk about Monty Python, but I'd like to tell you really a story of a series of pathways. There's no right answer. I hope the lessons learned from it will be informative and guide people, because I think we all craft our science careers in our own ways. It's a very intensely personal thing. I was lucky, maybe all of us were. I came here in a heyday. So I'd like to share some reflections about that and remind you two things. If you take only one thing away, throw rocks at me, I do like them. Remember two things. Number one, I think science is a destination. Engineering, technology, and all the things that go into letting us do what we do, those are the enablers. So people say we don't have a destination. Of course we do at NASA. It's science. It's always worked. And so we pursue knowledge through the tools that we have to work and live and extend our measurement space into space. So I'm going to share that with you. Mars will come up a bit. My kids did think I was from there until they got old enough to know better. So let me share that. So this is just my outline. Yes, I was a geek as a kid. I played various things, and I've had some interesting opportunities. This is the set of Jay Leno. This is not Jay. People ask me often. But I'm going to try to take you through the story of how I got to where I am now. Yes, I have talked to Will.i.am. He is a cool dude, and he does like rovers. But take you on the path. And the path is interesting, because it started, like for all of us, as a kid. And I liked weird things. I mean, you know, how many kids discovered the toad bug in Connecticut? Well, my name's on the discovery of that aquatic insect. When I was in high school, I was convinced it existed in the state of Connecticut. Looking for it in February was not the optimum, you know, biological environment. I always liked things that exploded, including the eruption of Surtsey. I was interested in where Columbus may have originally really landed. I like things that explode. Fungus is always among us. And I was fascinated by life at the edge. I show this big thing because as a geek, you know, we got beat up a bit. And I had a middle school challenge with some people. I learned that the power of these large voracious insects that look a lot like cockroaches can also deter bullies. I introduced them to a bully who got bitten ferociously and never bothered me again. So these things will suck a frog dry in about a minute, and don't recommend them, but they're apparently a delicacy. So the other thing that's important to me is to talk about how we get to do what we do. For me, I learned at a very young age, when I was a baby, this dog protected me. Anyway, I learned that we learn by sensing our environment, and our four-legged friends, whether they be feline or canine or, you know, bovine or whatever you like, they are great sensors, and as remote sensors, we use them. So these are just my four-legged friends in the course of my life as a scientist, and they've actually been inspirational to me. I hope you all have great pets. So the other thing that's important is, as we do science, we learn cool things. I think I first learned physics by being shot at, you know, 50 to 100 miles an hour by little black discs that weigh 5 ounces. And yes, it is bad to see a puck in the net behind a goalie. I'm not suggesting I was any good, but that was me in Bridgeport, Connecticut. And I once had a hockey coach tell me, and I'm not sure if he was being real or not, but on the 8th day, God made hockey. I kind of believed that as that, and I played in high school. It was really a grand thing. You can see no mask. I did wear one. But the message I kind of say is it taught me the value of these high energy collisions, which are so important as we look at this universe, this collisional universe that we live in. I always liked that stuff. So I wasn't particularly great at hockey, did love it, still do, but the collisional universe will come up again. Now, I went off to a very progressive educational experience I recommend to anyone who's thinking of places. I went to a university that's the color of something, actually named for a person who gave money, but anyway, and here I am with some of my acquaintances and colleagues. Peter Norvig, who was the Larry Bird of our Ultimate Frisbee team, is now the Vice President of Research for Google. Our friends and our colleagues, I find, at least for me, have massively shaped how I became a scientist. They challenge us, they help us, they yell at us, they demean us. They do things to make us better. And so my colleagues, even LJ here with his little six-pack, were great athletes, better than me, and they really helped me. Brown, for me, gave me the opportunities to innovate. Who can imagine their my sophomore paper for John Embry, the National Academician on Climate, on stochastic macroevolutionary models done for the first time to look at extinction rates across the Permo-Triassic. That was a sophomore project. Pretty cool when, you know, in the 70s. I mean, now it'd probably be nothing to do that, but it was neat to do it. I've also been shaped in, and we all have, by people that have let us do what we wanted to do. I was very lucky. I had two parents that are categorically not scientists. Really, probably never had science, and that's fine. But they let me be the geek that I needed to be, as many of us need to be. And you can see this was when I got my PhD at Brown, some 29 years ago, and they were, you know, they were tolerant of the fact that I probably was never going to make any money, but I would probably enjoy life. And as a scientist, I think at NASA, many of us have had that experience. So for me, that was very important. So I think it's important as we look at being scientists here at NASA, at Goddard, to remember the P's. Number one, it's all about passion. We should follow our scientific passion. It's always going to guide us well. It's about the people that help us do the science. And I've been lucky because those people have been great. It's also, in very many cases, about the places we learn to do the science from, at, or of. Places matter. And as a geologist, they matter a lot. You've got to get to know them to understand how they got there. And finally, the perseverance to actually do it. So I'm going to tell you that story. So as a grad student, of course, we're all left with challenging things to do. I counted rocks. I won't recommend it, but I measured rocks in places where their distribution, here on a pyroclastic cone in Mauna Kea and here at the summit of Mauna Kea, was informative. Informative about how the processes that we think shape Mars may have worked. And Tim Much, who was a NASA Associate Administrator and also my first mentor, said, go find Mars. You got to. If you don't experience it, you're not going to get it. So I looked for it. I also, in trying to look for Mars, discovered that Venus mattered too. Now, it is ironic that here I am with the bad shoes in Moscow, standing next to something about my size. Many people said maybe all grad students are about the size of robot landers. But in being challenged to look for Mars, the idea that comparing things would be important in terms of the physics and chemistry was really important. But more importantly, I learned a lesson that by pursuing Venus, this is a little view, see, SSSR in Russian, I learned something. The language of science really is everywhere. It knows no boundaries. We were at the point when I first went to the Soviet Union, not exactly in the most friendly relationship with our great neighbors across to the east. However, we pursued, rather engagingly, the questions of what made Venus work all the time. They shared data with us. God knows they tried to give me maps I never should have left the country with at times during an era. In fact, anyway, I'm surprised they let me out. I carried meteorites back from Sokhoti-Alin, for those of you that know about that, actually for the shoemakers, and they gave them to me. I walked through the customs with all the spravkas, the forms you need to get out, and they let me go because science was universal, and the Soviet Academy was very good. So, in pursuing places, trying to understand the processes that shape other worlds, Mars, the moon. I was taught by a lot of colleagues, women and men, that used this. This is SP Cone, right on the time when we first flew a laser altimeter across the Grand Canyon. We called it SLAP. I remember vividly, some guys in the room. It wasn't exactly eye-safe, but we were lasing effectively in the late 80s and managed to make measurements that helped sell a mission that went to Mars. We also did the first measurements of microtopography. This is when we set up our, when we set up our differential GPS site in Death Valley in '89, when there were only a few hours of enough satellites to even make a measurement. Now we drive to find, the Walmarts with it. But back then, you had about 2 hours, got up in the morning, the park rangers came, "What the crap are you doing?" We said, "We're measuring the, centimeter scale relief of rocks." And they said, "Why are you caring?" And I said, "Well, it matters." And they let us go. Science is universal, so we did that. You can see the great engineers that helped us do it, several standing around, but others actually working. I'm just kidding. And then the other thing I found in this universal language of science, that I was impassioned by the history of cosmic collisions on Earth. We knew they were caused biological crises. This was a big thing in the era that came out of the Alvarez papers that some of you might remember about global extinctions. And I was convinced the record in the last couple million years was not well enough known. So I convinced my friends in the Soviet Academy to mount an expedition, this is 14 kilometers across, to the biggest recent impact event in Earth history. An object the size of Bennu, which we'll be visiting with OSIRIS-REx, hit the Earth, and we measured its date. This is just a view looking at its big ejecta blobs. Hit the Earth 870,000 years ago. In a partnership with Berkeley, Goddard, and international colleagues from the Soviet Union, we measured the rocks of the last gigantic cosmic collision that hit the Earth that we know of in the desert of Kazakhstan, just south of the now almost eradicated Caspian Sea. So we went there in the middle of nowhere to try to understand that. Science allowed that opportunity. And really all it took was the passion to say, this matters. They didn't know how old that event was. We found out. It was a partnership, and partnerships matter. So I also remember being left on Surtsey the first time. It was a little interesting. The pilot of the Iceland Meteorological Service helicopter said, "We hope we'll be back tomorrow. If the winds are too high, we won't." But we went, they left our gear, we made some measurements, noticed these gullies, interesting little forebearer, harbinger of what we saw on Mars, now tens of thousands of places, as we started to look at the planet on the hillsides from the Global Surveyor and others. So I've been around to places working in different vantage points, in aircraft. Here's my good friend Dave Pierce. First time we did a GPS tracked mission in Iceland in '89. Pretty cool. This is all now routine, but we were starting out. And I like to show we have a bridge to nowhere. Well, here's the road to nowhere. In 1996, I remember talking to Gassim Asrar, and several colleagues said, Jim, there's this big festering eruption in Iceland. We see it seismically. And I said, yeah, we'll probably have the biggest flood in the 20th century. And in fact, Iceland never lets us down. We did. And Iceland, basically, these glaciers up here, Skithrajökull, back here in the background of the Skeethler Sonder. Skaftafet Park is over here. Basically, under the Grimsvötn volcano, bubbled up a huge volume of water, and out came a discharge rate the size of the annual rate of the Mississippi in 12 hours across this plain. Right over here, there are blocks of ice I can't show you, the size of buildings at Goddard, right here. But this road was Route 1, and it was no longer Route 1 for a while. And the power of the physics of what happens here on Earth can be applied to Mars. And so places matter. The other thing that matters are people. I can't mention all the folks that we've all been influenced by. I think we can all make a laundry list. I wish I could just go through. But for me, I was very lucky. I had professors. Tim Much first taught me a course about exploration as a freshman, who said, you know, dare to explore, follow your resolve, all those great words. Others, Jim Head, Richard Grieve. I was lucky enough to be hired by Noel Hinners, who was a center director here, also an associate administrator during the Viking mission. We Viking folks stuck together. It was great to have Noel have me come here. I was very fortunate to be asked to work with Sally Ride after Challenger. Sally was way cool to work with. Literally one of the smartest people I've ever met. Inspiring in every possible way, seriously. And of course, always the ever-challenging Ed Weiler, who pushed me to new limits by telling me in many cases, you know, that's not good enough. I don't get it. Tell me why we need this humongous Mars orbiter the size of a truck to figure out things and when we didn't need it before, and others. And in fact, it comes down to the people that matter, including, you know, my wife, my boss now, who listened in many cases when they didn't have to. They give us the opportunities. Science is all about seizing the opportunities. And I was lucky to have that here at the Saturn V exhibit at the Kennedy Space Center with some of the folks I work with on various studies for how to bring science into human exploration. This is something I was fortunate enough, thanks to Sally Ride, to get involved with. I feel passionately that science with human spaceflight and robotics together is our story. We've done it well with Hubble, with Apollo. We're ready to do it again. We're doing it on station. Let's go do it. And this was just, here's Doug Cook, if some of you know. This was during an interesting skunk works that we did called the Decadal Planning Team. Sounded like a shot I got from the doctor as a kid, DPT. But it was basically a prevision activity we did for the administrator. So, as part of science, I think we're also inspired by great places. For me, this strange monument, my wife and I were there 25 years ago, the Wapatki Monument in northern Arizona in the Painted Desert, is an inspirational place. It's mystical. Maya Angelou, and sadly who passed today, would have described it better than I. But it's a place where landscape and rockscapes and civilization all come together, the edge of a desert, hardly anyone visits. I went there, you know, literally when I was first starting here at Goddard as a NASA scientist, and I then later took my kids back. Because I wanted them to feel the connection to the people that lived there 500, 600, 700 years ago, because I thought it really was an important element of just understanding things. As a geoscientist, it mattered to me. I also think sometimes the written word is very important. When my son was 8 years old, he showed me this poem and said, "Dad, this sounds like you." You know? I said to a squirrel, "What are you carrying?" He said, "It's my lucky rock, isn't it pretty?" And I held it and said, "Indeed." And I said to God, you know, "What is this earth?" And he said, "It's my lucky rock." And I thought the planets are our lucky rocks that we know about. And there's billions, if not countably too many for me to describe out there as we discover exoplanets and understand what they mean. You know, countably trillions of other small objects. But anyway, this great, you know, poet from the 17th century, I think, captured some of the spirit that we all have when we're scientists. So the other part of science, writing the papers, making the discoveries, extending knowledge, building the legacy, is talking about it. Sometimes we're reticent to communicate what we do. I understand. It's scary. You know, I have had members ask me again and again, members of our you know, why are we doing this? It's a waste of money. And that's their right. We have a privilege. So I've been lucky enough to be allowed to help promote what we do. And by promoting, we've actually given us the possibility of doing great things. I've promoted by going to places, filming a show in Iceland right here at Lake Kleifjordvatn. Just imagine this dry, that would be Mars. This place in the Reconnaissance Peninsula in Iceland is spectacular. I urge you to go there. You can wander right up to Boiling Springs. We filmed for Discovery Channel there, fabulous place. Of course, I've been to Surtsey, and you know, when they leave you there and say, "We hope we come back," you do wonder about the 60 kilometers from the mainland, you know, but it is a cool place, and 50 years old now, pretty neat. And of course, we get to go to cool places. So we did sit on the set of Jay Leno. This is Bill Ingalls, the chief photographer at NASA. That's not Jay, as you can tell. I'm not as good looking, and I don't have a motorcycle. But we did get to sit on the set, and we were about to go on the Jay show, some of us, and that fell through various, scheduling things. They had, someone important like Beyonce. I don't know, someone of that ilk. But I did get on Letterman, right, during the snafu with Spirit and the file manager system. And it was incredible because I followed Matt Broderick out on stage. And apparently Dave was scared to death of having a geek on. And so he really tried to, bemuse the audience with me, but we had a good time of it. And communicating sometimes requires that. So I was lucky enough to do that. But I've also been involved in communication programs that really stretch the imagination. When I was the agency chief scientist, they asked me, would you support a program that looks 100 years out to biomimetic robots that would explore other worlds around Alpha Proxima or one of the nearby potential exoplanetary systems? I said, well, I guess. And they said, you and Hawking are going to be on there. I said, okay, I mean, that's good. I don't know the man, but he is great, read his books. And so we did this program that took biology and geoscience and planetary exoplanets and put them together. And it was really cool to do it, to try to see what the artists were trying to depict from how we were describing what could be. And we know we're not right, but at least it was a lot of fun. So the final part of inspiring and communicating is communicating down to those that will become the scientists that we all are, or the engineers. And so bringing a little piece of Mars to show the young folks, extending their view to see what we've actually done. This actually is the spare mirror at JPL with my son, who's exploring, at JPL. Doing this during the mission, sitting in mission control with kids, letting them see it. A lot of young women came by to see. And then extending that passion to them. It's always gratifying to see, even though you're not allowed to talk about it, they still get it. And so my kids actually love science, even though, rocks were out. And they both like the biological side of things. And since we're living things carbon-based, it's probably a good thing. But passing on the flame to students, grad students, postdocs, undergrads, middle school is critical to extending what we do. And also passing on to our elected representatives. And our good friend Congressman Culbertson here looks a lot better than me, but he's been a real passionate advocate for what we do in space science, and really helping him reach his other members is critical. And we do that here at Goddard, we do it at headquarters, do it at JPL and all of our centers. This is an important part of the privilege we have to do our stuff. And then finally thanking those that got us to where we did. I was lucky enough to be able to thank some of the folks that allowed me to be a scientist at Brown a few years ago as part of events there. So lastly, sometimes you get a very unique opportunity. A few years ago, I got called by the administrator and said, hey, could you stand in for me at Google Zeitgeist? This is an event Google holds where they bring in the movers and shakers that they want to interest in what they're doing. And I said, well, the only thing I can talk about is, like Mars. Do they really want that? And they said, oh yeah, you're gonna go on, right before Al Gore. Oh, I said, great, that's good to know. The undeniable truth that it is. So anyway, while I was sitting in the green room or whatever color it was, there at Google, which is way cool, we talked about climate change on Mars, pretty interesting stuff for those of us that like it. And Al said, yeah, I didn't know that. And really, he was inspiring, and I talked about Mars, and people seemed to like it. And then we had a guy after Al Gore do card tricks. So it was an interesting event. Science to vice presidents to card tricks. I can't do any, but it was good. And finally, we sometimes get opportunities to interact with those that really are famous. I have not met Beyonce, I'm sorry. But I did get to talk to will.i.am during the landing of Curiosity, which was really way cool. And he was really gung-ho. This is a model. You can just see how big our girl is on Mars. I mean, really a big thing. So pretty cool. So I've had a very different career than many scientists here at Goddard. I had the opportunity and also the disadvantage of following a different path. I didn't get to just sit here right at the peak of an experiment that I was partly responsible for. I didn't get the chance to actually execute some of my own science because I was called back to the front to help sell the program that we've had in Mars. And in '99, when I got a call from many people saying, Jim, that drive to DC isn't that bad. Really not that bad. I was called to duty. And it gave me an opportunity to work with some of the very best NASA headquarters has ever had. administrators and associate administrators that wanted to do science with incredible passion. People like Ed Weiler, Ghassem Asrar, of course Dan Golden loved Mars with passions as well. And by having that, was able to actually have an influence. Not always, you know, I wasn't happy here when we had a little fault problem on the rover Spirit, but it gave me a chance to do some pretty cool things for the community. And giving to the community so others can do science is really part of the equation. So in the next 10 minutes, let me just tell you what I was lucky enough to be part of doing. In 1999, if you all remember, there were 2 craters on Mars formed by human beings. As Ed Weiler said, he inherited the craters, not those made by Mother Nature. Not a good thing for an associate administrator and NASA at a time of funding issues. So the Martians came out of the woodwork. As we said, all of us who had worked on Viking, and many of us came back. Tom Young, Jim Martin, who some of you knew from Viking, Gentry Lee, myself, all of the old Martian dudes and dudettes came out, and we put together a program that we thought really would be dazzling. It's a campaign to study Mars like our Earth observing program. And that program was totally restructured, building off what we had been doing on the Global Surveyor with instruments developed here to move forward through the lens of even what I call Earth-style reconnaissance into landed laboratories. And I remember going to OMB in January of '01 and saying, we need to land the equipment that we used to study Apollo rocks here on Earth on Mars. And they said, we could do that? I said, well, we think so. The engineer's willing. Science is always willing, I think. We're pretty imaginative. And so we put in place this program. And initially people said, yawn, it's boring. Well, now, $7.8 billion later, I think people think we've done pretty well. We've generated a half a petabit of data. We're exploring Mars with instruments that are so sensitive we can detect, thanks to Paul Mahaffey's team, we can detect contamination of Florida in the instrument on Mars, knowing that we didn't find Mars that smells like, Kennedy Space Center. And the program has given us opportunities to do new things, explore what we can do with Curiosity now. And you can see all these green things about the successes we've had. Since we restructured this program, we have had a success rate that, any of you know what GIPRA is? It's a rating system for how government programs do. Mars several times was the #1 ranked program in the federal government for performance. Not bad as an engineering management science program. And we've had other successes at NASA too. So we put it in place. But it all started for me with the little intrepid global surveyor about the size of your refrigerator. She had some problems getting to Mars, but once she started going, she produced a legacy of information that to this day really, I think, fulfilled my vision. This is a 3-dimensional image showing a large polar crater with a giant sheet of ice inside it. The polar ice cap here in the north is there. This is the crater Korolev. The reason I show it to you is Korolev is another hero that we forget. Korolev was the Ukrainian Russian rocket scientist, like Goddard, like von Braun, who brought the big boosters to the then Soviet Union. And he built the core engines that we're using in our Atlas rockets. His design team, they actually started with Korolev. So pretty cool. I went to his gravesite in Zhytomyr, a little town in the Ukraine, just to commemorate the dude, because he was pretty cool. Tried to build very big things. We also had the chutzpah to ask for a mission that Mr. Golden even said, break it up. We asked for a mission with a wingspan bigger than this room, to carry cameras the size of telescopes we'd look to look at other universes. And people said, why? And I have to say, took a lot of grief for this. MRO, the Mars Reconnaissance Orbiter, is a big girl. And she's done a lot of stuff. Her whole goal was to link the Mars hydrologic cycle to the climate state and to the way in which things could be preserved on the surface, to find the landing sites for the future missions to eventually bring things home, in a nutshell. However, MRO was big. Mr. Golden liked faster, better, cheaper. We were going bigger, heavier, more expensive. And not exactly his theme, but we prevailed, we persevered, we sold it. Recently at a meeting I went, and several people that literally shouted me down every time I stood up to say, we have to fly MRO, said, Jim, hate to say it, you were right. We can never go back. We can now watch the wheel tracks of our rover to plan where we go. We have situational awareness to make choices that we never had before. This is better than we had at Apollo because of this science mission. And so it was very funny when President Bush's team were starting to look at the vision, they came to me and said, what's the first thing we could do with the moon? Well, of course, we wanted to bring back samples. We wanted to do geophysics. We wanted networks, all the great stuff. I said, no, we need an LRO. And they said, a what? Could you spell that? I said, we need a reconnaissance orbiter at the moon to open up the frontier to know what we should do. to follow the volatiles, to look for all these things. We need to do it the way we did Mars. So we're ready with our eyes wide open, our robots and people wide open to go. And so this mission, thankfully, was given to Goddard, a brilliant move by headquarters. And I led the team that competed the payload, and we put 9 instruments on there that opened the lunar frontier for us. And I like to show this picture. That's me silhouetted against the moon in 3D. But I show the picture because when I first got to Goddard, we wrote a proposal called Lola. Now, Lola's a good name. She always gets what she wants. We wrote a proposal to do a laser altimeter, and we had reviews, several of which were rather demeaning. But we got a little money. We converted Lola into Mola. And then later, Dave Smith, Maria Zuber, Greg Newman, others in this room came back, and they gave us Lola at the moon. And it was really rather cool. For me, this picture from a young crater that I'm hoping to be named after Charlie Schnetzler, that used to be here, was spectacular because this is the view of a fresh ejecta blanket around a crater that formed yesterday. Scale here is a few hundred meters across. You're seeing the curtains of ballistic sediment that flew out of a hypervelocity explosion on the moon, where they're preserved for millions of years. Well, so we think, and this is really cratering physics in the best. So I like to tell a story. Right when LRO was launching, Rich Vondrak said, you know, Jim, did you know that Robert Goddard wrote about the moon? And he actually spoke about it at his commencement address in Massachusetts in like 1918 or 17, somewhere before my time. I'm old, but not that old. So Robert noticed this crater called Leno, named for Linnaeus, the Swedish taxonomist, and he said, oh, it's a big volcano, the moon's erupting, isn't this great? And well, since then we know differently about the collisional universe, and these are some of the graphics, the images made by instruments on LRO that have peered into the way these things assemble themselves, shown the character of the blocky ejecta, the conical cavities. This is Lola and imaging. We've seen differently. We've learned and improved upon Dr. Goddard. For me, one of the passions I've always had was trying to understand this collisional universe. It's driven me to be interested in small bodies that collide with planets, you know, like Bennu, to watch this production rate of craters on Mars, where it's clearly a hot place. We just drove by a couple of giant meteorites with Curiosity, for those of you who've been following. Pretty cool, like masses of iron that big, spallation products probably, and our craters on the Earth. And this, to me, is one of the reasons why I became so intrigued by this thing. This is the most recent giant impact on Earth as seen by SRTM, and it doesn't look like a crater, because it landed in a target. It didn't land. It collided with incredible kinetic energy in a target that relaxed upon formation. The rocks there were volcanoclastics and wet, and it, we think, relaxed and produced a structure which, even at the best of viewing, is a very narrow ring of hills you can see there. And we of course, came up with the radiometric age of it. But this is the most recent large impact in Earth history. We think the likely yield was 20,000 megatons of TNT equivalent. Just for scale, folks, that's pretty much the nuclear arsenal of most first world countries. One event, 870,000 years ago. So we're due, folks, as we like to tell several people, but this kind of thing happens all the time. And the consequences on the Earth climate and other things regionally are very interesting. The other thing that I think Goddard has given many of us, and I've been so fortunate, is the ability to dream of what we want to measure, then have engineering, and in this case, human spaceflight, make it happen. So I came here, you know, with much lesser dreams than Dr. King. My dreams were to measure the topography of the landscape at very fine scales, to understand subtleties of it, to compare Earth to Mars to Venus, blah, blah, blah. Okay, won't bore you with the science. I've always liked that stuff. And so I came and said, can we do that? Can we remotely sense the scale that we would walk on? And the engineer said, well, of course. You actually want that? I said, yes, I really do think we need that. It's really important to understand, though. It's how the water flows, you know? And they said, oh, well, we can do that. We can do it with lasing technology, laser technology. So a team of us, some are in the room here, were lucky enough, thanks to a Goddard Director's Discretionary Fund initial grant and some spare parts from Mola 1, to fly twice in the space shuttle. Here's Discovery going off in August of '97. Previously, in January '96, Endeavour went off, and we flew the shuttle laser altimeter. It was the first analog waveform echo recovery LiDAR in space, and it measured stuff that was cool. We started to get returns like this across the western US on SLA2, and we realized that we were actually seeing the ground and the treetops. We realized we could measure structure of the fuzz on the Earth as well as geology, and we could see how flat the deltaic plains are on Earth, which are, by the way, storm surges, really a problem on the great deltaic plains of our planet, where scale of 100 miles, they vary by a meter. So you can imagine what a little storm surge would do to people living there. But we were able to do this before we actually got to Mars with Mola, before we flew ISAT-1 as GLASS, and really gave us the inspiration to think of how could we study this aspect of Earth science. And it was the engineers and a little push from a few of us wacky scientists that gave us the opportunity. The other wacky opportunity I had, and I remember Ed Weiler's look of great disdain, when I said, you know, we're going back to the moon, this time for good. You know, President Bush's vision for space exploration, we have to use Hubble to look at the moon. And Ed said, Jim, you don't want to do that. And gave me a lot of great grief. But thanks to some great engineers here at Lockheed Martin, up at the Hubble Space Telescope Institute at Hopkins, we looked at the moon at 60-meter resolution in very highly calibrated ultraviolet wavelengths near UV, and we're able to actually extract signatures of titanium dioxide-bearing materials, which actually would be a resource on the moon because they're so enriched. Some of the lavas on the moon have, you know, up to 10 to 15 weight % TiO2, which literally would be an ore body here on Earth. But Hubble's calibrated sensing, which is great for the UV universe, is also really good at the moon. None of our orbiting remote sensors had anything with that quality. Just getting it to target the moon, though, was an engineering dance of incredible, I mean, really an incredible feat. So I want to finish in the next 10 minutes with sort of how I got to where I am now. So I like landscapes. Here's Gene Cernan on the moon, Doris Littrow. Here's little girl Opportunity with this massive curbside crater she landed in. Literally, folks, it's this tall. Just for scale, so you don't forget. We've seen much bigger stuff at Gale, but I have always been searching for what these landscapes, how they connect at the level of the microscale geophysics. How do they get to look the way they do? These missions that I've been fortunate enough to be a part of or to have helped promote, from Viking when I was an intern and took the first course in geology of Mars at Brown, from Tim Much, through the Global Surveyor, where I was its longest serving program scientist, to putting new instruments on Odyssey that came from other countries, to being the first geek who had the guts to say, you know, we have to do this. Ed Weiler turned to me at the meeting in May 2000 and said, all right, science, that's the way Ed talked, science, what do you want to do with your Mars program? And Dan McLeese and I and several others looked at each other, and I said timidly, we kind of want rovers, Ed. And Ed said, what was that? I said, we kind of want rovers. And Ed looked at me and everyone else think, but if it fails, we're doomed. But engineers are great. They've always made things happen. Of course, 2 total successes beyond the warranty really bore fruit. We've also flown MRO, supposed to last 3 years. We're now on 2014, so still going strong. Phoenix worked, LRO still going, and of course, Curiosity is amazing, and we're planning 2020. So, sorry about that. So let me just recap then. For me, I came to Goddard, and we had flatland Mars, and really cool place. Climate, rocks, ancient, interesting planet, now dead. And thanks to the engineers here and a few of us scientists, we turned Mars into 3D Mars, but more than 3D Mars. This wonderful view, a map made by Greg Newman of the 600 million measurements by Mola that flew on the Global Surveyor, is more important. It actually gives us the ability to access places on Mars. We know where the ground is. We can design engineering solutions to go to places that we didn't know before. So Mola has been a science and an engineering tool. I've made measurements. I won't bore you with them. These are the shapes of craters all across Mars that tell us something about targets. I've also been interested in things at a very small scale. And this is where the grad student in me has never escaped. This was the first picture we took upon landing on Mars. This is the picture from the descent imaging system. It's a video camera that weighed 500 grams. There she is, little Marty. And Marty, when we landed, the dust is flying and the rocks are flowing, took this picture. Actually, several hundred of them. We averaged them up, and you can see a 2-inch little pebble here. And we thought this was great. And then we had the creative idea of, as we drive, we can take images. And if we take them at dusk or twilight, a lot of the dust coating on the lens will be not a big factor. And then we can do classic, for all of you who took geology and took sedimentology, you measure the shapes and sizes of rocks and you figure out how they got there. It's a little problem in physics. So we've been doing that. And we put together sets of now that's dozens of images as we've driven across Mars with millimeter resolution. So you're seeing things down at the granular level. This is when we started doing that in earnest. We've gone up to day 640. And we've used that, I won't bore you, except to say we can now start to correlate with distance from source. We've been driving along here to get up into here. Correlate the sizes and shapes of rocks with distance to start doing basically hydrogeology by just counting rocks. It's a great task for a bullpen of students, but some of us have to do it. This is one approach to trying to understand how this surface put itself together so we know where to sample. And of course, there's also interesting things we've seen along the way. I love the old couch rock, or whatever you want to call her. This is one we saw back on day 533. And here's one that I snapped in Heimaey in Iceland last summer to show you similarity. This is about twice as small as that, but these are layered palagonatic rocks from Iceland, really cool place, and some of the similarity is striking. So one of the things that I've tried to do is connect what we do on Mars to things on Earth. And one of the best places to do that I was trained to do is Iceland. And here's yours truly freezing his butt off in Iceland in October. It does get cold. This is the grand island of Surtsey. When I was a little kid, it erupted, and my grandmother, who lived to be over 100, said, "Wow, Jim, volcanoes erupting out of the sea, it's new land." And I thought, wow, you know, I was all of 5. Pretty cool. And it struck me as something I'd like to know about. So we've been studying Surtsey ever since I was in graduate school and was inspired by Richie Williams to do so. This is a high-resolution radar map. We make one every 28 days with RadarSat. And we try to track what happens. You can see the northern spit moves around because it's on a socle. And we measure the textures of the rocks once every few years. There's a GPS leveling line that goes across here. There's a drill hole right near the little hut. And so we're monitoring this place. These are the gullies. And many of these rock patterns in these conglomerates and cemented rocks are similar to things we've seen on Mars. We're also watching Surtsey go away. Sad to know that when she was born, here she is, and little plots, and we've been tracking her with aircraft laser altimetry in the late 90s and early teens, and came up with basically I call it a punctuated equilibrium erosion model, where you pulse it every so often with big sea state changes and Arctic storms to erode more quickly. And sorry about that. And we produce a model that shows that Surtsey, it stayed in the 2030s and how long it could last. We think what will end up happening is just a couple sea stacks will remain protected by this pelagonization process that makes things as hard as cement. OK, so let me conclude in the next couple minutes. So for me, I've been on a voyage. I was lucky enough to have affiliation with the Viking project as a student, undergrad at Brown, grad student, and thereafter it paid for my graduate education, so thank you, Viking. I did come from Mars. And Viking had 3 footpads. So we had 2 Vikings with 3 footpads. Now we have 2 times 3 is 6. Now we have 6 wheels on a big rover carrying instruments that the Viking team are inspired by every day. The person who built the mass spectrometer system on Viking said, "You can't believe we have something as good as SAM flying now on the surface of Mars," with imaging systems that literally were inspired by James Cameron and built by Mike Malin. So this has been an evolution. I was lucky enough to have presented the idea for Curiosity to the Office of Management Budget in January 2001 with Scott Hubbard and with Ed Weiler, and they believed us. They trusted science and engineering could make this happen. We did it, and we talk about it. Recently, I gave a talk, and Mars is flying here, apparently out of my reach, but I'm still going there and trying to inspire people. I went to this TED thing, and you know, most of the people who speak are inspirational people that have solved massive social problems, and I was talking about Mars. But that's what we do. And as scientists, that really helps, I think, explain this investment. And I've always seen science as an investment. So where am I going? Well, lucky to be here. And thanks to all of you, and I'm your advocate, please talk to me. But I'm still struck by a problem we have. We've got a tail, it's like 3 bears. We've got a tail of 3 big rocky planets with atmospheres and climate systems in our little neck of the woods of a semi-random, or whatever you want to call it, solar system. And they aren't at all alike. And somehow the disparities between what we're learning about Mars and what we know from our Earth science program and terrestrial science here on our own planet and Venus is crying out to tell us something. And we haven't been back here since the in situ mission of '78, known as Pioneer Venus, and our Magellan mission of the early '90s. We've abandoned our sister, I would say. We like our brother, you know, he's kind of cool. But our sister is just waiting. And so getting to Venus is one of my passions. We've got to get Venus into the equation of how these things work. We've been trying collectively here and other institutions, the Applied Physics Lab, JPL. We've got to get back, because I think we're missing something. And whether it's the chemistry, the evolution of its crust, the interior, climate change, it's all there. And Venus is ready. So I'd like to see us get back. Obviously, the state of knowledge of Venus is this. So here's Meteor Crater. That's a nice little view. That's what it looks like at Magellan resolution. I don't think, I mean, unless you're more imaginative than I or have had something much better to drink than I, you would probably write a paper about that. This is what we can do now, trivially. the capabilities for measurements of many kind, in the infrared, in radar, this is an instrument developed by our friends up the road at Northrop Grumman Electronic Systems, are amazing. We're ready to go back. I hope we can. Finally, a couple years ago, leaders of our center asked many of you to help me collectively put together a vision for Goddard 2035, 2040. Where do we want to go? What do some of you young folks want to be doing when you're as old and gray as me? And this was one of the inspiring things I saw from that. The idea that it's the intersection of these science spheres as we solve problems about where things could have been living, where their records could have been preserved. To me, this is really who we are. And it integrates the astrophysics of exoplanetary systems with how we live with our own planet, our own parent star, to how Earth science informs how we have to detect the science of these processes, to what we can do across the solar system, not only at Mars, of course I mentioned Mars a lot, but Europa, Titan, Venus, all the places. This is an integration of science. We can do this. We can. This could be a vision. We could be doing this in earnest. So I remind you of what it was like in 2004. 2004, Ed Weiler and I were asked to talk to then administrator about where we should be going with this president's vision for science. And so Ed and I made this chart. I'm not saying it's right. It's a framework for talk in front of people that make decisions worth a lot of money. And we said, well, there's lots of questions that are interesting. Understanding can grow. And their impact over long time scales is a metric it's hard to measure. It's not like how fast a tree grows or how fast we grow or whatever. How fast the Redskins win the Super Bowl. I mean, if that's even a parameter. But in any event, so we put some things down here. We talked to some colleagues, and we said, there's a trend. If we could get people and machines together in the pursuit of science to these places, to the bigger universe, to those exoplanets, to Mars, maybe to Europa and Titan, we'd be higher up on the curve as we leave our home system and our nearest neighbors. And we said, it's all about basically what we said here. We said it here. We need to start thinking of things that connect the dots. And yes, we need to do these. Of course, we can see all these things with that technology. But we can do more here and maybe, and of course, more here. So this was just an idea we had. So in closing, science is what I've done. I've been very lucky. I have a lot of dreams. And really, I've been very fortunate. Many have been fulfilled. But I love this dream because it sort of says it all. It's engineering technology that lets us do the cool stuff, to go to the places we need to go, some still inaccessible, some unimaginably long in terms of time, and carrying with them the systems that will extend ourselves with measurements that we never thought we could make. And we've been doing that here on Earth since NASA was born with the first weather satellites, satellites for geophysics, understanding the surface of the planet. And of course, this was the model of JIMO, the nuclear electric propulsion system that could have visited all the satellites of the Jovian system with one propulsion system. New engineering, new technology. IT that we use now that pumps back a petabit from the moon didn't exist when we first went to the moon with Apollo. A petabit from LRO. So I'm reminded of the great artist, a modernist, not a scientist, George O'Keeffe, who painted the ladder to the moon in '58, right as NASA was born and we started on our voyage. And she meant something from the hillsides of New Mexico and this ladder that I think embodies technology. But I think what she was saying, cast now to the 21st century, is, we had a ladder to somewhere back then. We were going to the moon. Great target. Great science. But I think science in general is our destination. The engineering to get there, whether it's a ladder flying in space, or a space elevator, or a slingotron, or nuclear propulsion, or literally immersive virtual reality, sending ourselves there. One guy once said, maybe if we just sent our heads, it'd be less work, was really what it's all about. So I like to tell the kids, our job is to do science, but not to tell them what to foresee. Saint-Exupéry said, we can't predict the future. It's not really our job. But we have to build the bricks to enable it. That's the science I've been lucky enough to do over a long time at Goddard. And so don't wait to wonder. It's always there. This is just a picture. Literally every day we get a present from Mars, from the universe as we look. This is just a picture of something that to me as a geologist kind of gets me a little fuzzy. Pretty cool. Never would have thought we'd see that after Viking in the fields of impact-derived ballistically placed rocks. But this is Mars now every day for us as we explore. So I'll stop there. Just look at our little octahedrite we've discovered on Mars, and take questions and comments. I thank you for listening to my boring story. Thanks. Yes.